Welcome back. Today we're going to be talking about our first actual unit with physics content, not just math, and that unit's going to be motion. In physics, we call the study of motion kinematics. It's really just a fancy term for studying motion, but we're going to be describing how an object moves through space, not specifically outer space, any space. When we look at motion, when we talk about kinematics, we're only looking at the motion itself. We're not worrying about what causes it, why an object has that specific motion, not looking at the forces involved. We certainly will do that this year, but not in this first unit. But as we go through, we're going to be coming across two different types of measurements, and we've mentioned these before. We mentioned these when we were talking about some of the different math we're going to be using. We're going to be using our scalar and our vector quantities. And as a refresher, our scalar quantities are measurements that are described completely by magnitude. So 50 grams, 30 volts, something like that. Whereas vector quantities are measurements that require a direction in order to fully describe them. So particularly with movement, we add a direction into that movement, so 50 meters east or in a positive direction, something of that nature. So as we said, our vectors have both magnitude and direction. Think about an arrow, right? So we draw an arrow, but here's our line. It's not yet an arrow. We have to add an arrowhead. That gives it a direction that it's pointing. And so this particular vector right here, this particular arrow that we just drew, is not the same as this one right here. And not just because I drew it in a different pen. The lengths may be the same, so the magnitude of each one is the same, but the directions are opposite, and so they are different. Let's go back to this. So the length of our vector, the length of our arrow, and we're going to use arrows to represent vectors all year. And the length of that arrow is a relative description of the magnitude or the size of that particular measurement. And then the direction the arrow is pointing is the direction of that measurement going. Now, in this particular unit, and as we're talking about kinematics, there are three very significant vectors that we're going to be talking about: displacement, velocity, and acceleration. And we're actually going to be using these all year. We're going to learn about them initially here, but they're going to come back for the entire year. Displacement, the magnitude, the measure of displacement is distance. And we're going to talk about the difference between those two terms later. And then it has a direction. Velocity, the magnitude of velocity is speed, something that we're probably familiar with. And then acceleration doesn't have a scalar component other than the measure. All acceleration measures are vectors. Now, as we make these measurements, we have to consider what we call our frame of reference. And a frame of reference simply tells us where the origin is, where the zero position is. It also gives us an indication of which way is the positive and which way is the negative direction. And the nice thing about our frame of reference is that in most cases, we can pick our own frame of reference. So if we have an object starting to move in the middle of the room, we can call that middle of the room position 0. We don't have to measure how far it is from the edge of the room. We can set our frame of reference as the starting position is 0 and go from there. We can also pick our direction. If I'm working on something where the motion is primarily downwards, so something's falling, I can call down positive and up negative, and that's going to make my calculations typically a little bit easier, a little bit more straightforward. The key to using and establishing a frame of reference is that you're consistent. However you set your frame of reference at the beginning of your scenario, of your problem, of your experiment, as I said, it can be whatever you want. You just have to maintain the same frame of reference throughout. Now, in this example down here, we have no idea where this car is actually starting, but we're going to call its initial position 0. We're going to say to the right is positive. We can call up positive. Left is going to be negative, and down is going to be negative. And so now we have our frame of reference for movement, and so sometime later it's moved in the positive direction. This change in position that we're going to measure is what we call the displacement. Okay, displacement is the change in position. It's the distance between where an object starts its motion and where an object finishes its motion, or where it is at the whatever time we happen to be actually measuring its new position. And so mathematically we say delta x equals x sub f minus x sub I. And in this equation, this delta, and you might remember this or recognize this from math class, our delta symbol simply means a change in. And we're going to use that symbol a whole lot this year because we're going to be measuring a lot of changes in different measures and different quantities. And then the actual equation itself, x sub f minus x sub I, we tend to use x or sometimes y as our symbol for position. And then in physics, with our variables, we use subscripts frequently to indicate specific quantities of something we're measuring. So the x subscript f is final position, where x stands for position, f is for final, minus the I, which hopefully you figured out stands for initial. That was weird. And the x is again for position. So delta x is our change in position, and anytime we're measuring a change, it's always final minus initial. So we're subtracting the initial position from the final position. In this case down here, we have our car starting at 2, and let's say this is 10 meters, so delta x equals 10 meters minus 0 meters, so delta x is 10 meters. And the x. Now, the tricky or significant thing about displacement is that it's not always going to be equal to the total distance traveled. And so let's look at what we mean by that. Let's say we have a dog, or cat, I guess if you're a cat person. Dogs are better. If a dog runs 10 meters to the right, so let's say he starts here and goes 10 meters to the right, gets his ball, and then runs 7 meters back. Okay, let's say this is our total travel. This is our total whatever's happening. You throw the ball, dog runs, gets it, comes back. In this case, the total distance that the dog has traveled, it's gone 10 meters away, 7 meters back. So the total distance that the dog traveled is 17 meters. Okay? However, as we said before, displacement is the total change in position from start to finish. The total displacement is measured from start to end point. And so in this case, it's only going to be 3 meters. And because displacement is a vector, we're going to say 3 meters, either positive 3 meters or 3 meters to the right, or if we're on a map measuring stuff, we can say 3 meters southeast, if that's the direction that they were going, doesn't really matter. Okay, so Displacement is how far from where they started and in what direction. The other piece of this is that if we have established our frame of reference and this is the positive x direction, that would make this, oops, let's write it in a color you can see, the negative x direction, which means that our guy down here driving to the left in our frame of reference has a negative displacement, right? And again, mathematically, we can see that because the final position is going to be a smaller number than the initial position, and so your delta x then would be negative. So while these terms may seem similar, they're actually quite different. Not quite different, but somewhat different. Distance is scalar and refers to how much ground an object is covered during its movement, while displacement is a vector referring to how far out of place an object is from its original location. Okay, it's basically the object's net change in position, and with our displacement, as we mentioned, the direction does matter because it's a vector. Now, one other example of this, let's say a student walks 4 meters east, so 4 meters, not a significant distance, and then they walk 2 meters south. Now, I've established my frame of reference as north, south, east, and west, so traditional compass. Then the student walks 4 meters west and 2 meters north. Now, if we look at the total distance that this student traveled, it would be 4 plus 2 plus 4 plus 2, which is 12 meters. So that's our distance. But you notice that they end up right back where they started. And so because they are in the same place they started, if this is our origin, xf minus xi is going to equal 0. So your total change in position is equal to 0 meters. So your displacement is equal to 0 meters. Now for right now, we're only going to be worrying about vectors in one dimension. So along a single axis, along the x-axis or along the y-axis. And that simplifies things a little bit because it means that we can distinguish between directions using positive and negative signs. And again, it doesn't matter which direction you call positive as long as you call the other direction negative. So if I'm calling down positive, then I have to call up negative. If I'm calling up negative, then down becomes positive. And the same thing for our x-axis. If we call to the right positive, then to the left is negative, but you don't always have to do that. That's our traditional XY coordinate system, but if it's easier for calculations and easier for you to use left being negative, or left being positive rather, and right being negative, then you can do so as long as you maintain that frame of reference throughout. Eventually, we'll get to two-dimensional vectors, and at that point, we're going to use trig, and we're going to break it down to components, and all of those good things. But for now, we're not going to worry about that. Our second vector of the day, then, is velocity. And velocity is the time rate change of position. And what that means is it's simply the change in position over change in time, which is what we have down here. So our average velocity, then, is the total change in position, or the total displacement, which is delta x, divided by the total change in time. And so again, displacement, final position minus initial position. Time is final time minus initial time. And unless otherwise stated, our initial time should always be 0, because that's going to make things a lot easier. If we have multi-step problems, we might have to use a non-zero initial time occasionally. But again, simplify your calculations as much as possible. use initial time being 0 whenever you can. Clearly it's not the beginning of time, but it's the beginning of a time. So, the term that we're typically familiar with is probably speed. You may have heard velocity before. If so, fantastic. And while the two terms get used interchangeably, they're not exactly the same. As we mentioned earlier, speed is a scalar quantity, and speed is actually just the magnitude of the velocity. And so when we talk about velocity being a vector, the scalar component of it, the magnitude, is the speed, and then it has some direction, making it a vector quantity. We'll look at graphs here in a moment. What we'll see is that velocity is actually the slope of a position time graph. On those position time graphs, the tangent at any point is what we call the instantaneous velocity. It's the velocity at any one instant in time. Think about your speedometers on your car. Those are giving you the instantaneous velocity, or at least within a range of plus or minus 5 miles an hour or so. So we have instantaneous velocity, which is at a given instant, and we have average velocity, which is the velocity over an entire trip. And if you've ever driven anywhere in this area with all this red lights and traffic and everything else going on, you're probably quite familiar with the fact that your instantaneous velocity on a trip is not ever going to be the same as your average velocity for an entire trip. Now, a little bit more on these graphs, and we're going to be making lots of graphs. And we've mentioned the idea that graphs are going to be our models. They're our mathematical models of physical phenomena, and they're going to be a great way to describe what's going on, to describe phenomena, and to hopefully see it and interpret it a little bit more easily. So we have two graphs we're going to look at. First, we have a uniform position graph, and this is a great graph, hopefully easy to understand and interpret. This term uniform, hopefully you recognize, means stays the same, right? So if something is uniform, it doesn't change. So if your position is uniform, that means that your final position is equal to your initial position. And so graphically, it's going to look like this, right? The slope is 0, and our slope in this case is going to equal delta x over delta t, rise over run. And because there's no change in position, there's no rise, so there's no slope. In this specific situation, the initial and final positions are the same, and this x sub 0 is just another way to write initial position, so don't let that throw you off. And then also, because it's not moving, there's no velocity, so the velocity is 0 meters per second. This last piece is what we call acceleration. We're going to talk about that a little bit later. And then our second graph is when we have uniform velocity. So when the velocity is staying the same, when it's constant. It's changing the same distance during each unit of time. Now here, some things to notice. And we'll talk about some of this in class, and hopefully you're taking notes on things you have questions about. So our rise is change in position, our run is change in time. Here we have this nice linear relationship. Now this happens to be proportional as well because it's passing through the origin, but not all of your position graphs are going to be. The key to uniform velocity is that the slope should be constant. It's not necessarily going to run through the origin, but it might. So in this example, delta x, and actually let's write an x here just so we don't get too confused, although d and x are the same thing in this case, okay? So velocity is equal to delta x over delta t, which graphically, if we look here, delta x over delta t, that's equal to the slope of our graph. And we mentioned that a few minutes ago. The slope of a displacement time graph is our velocity. Because the velocity is constant, the initial velocity is equal to the final velocity, which again then makes our acceleration 0, but we'll talk more about that later on. The other piece to this though, and here we have a nice positive slope, but if the object suddenly switches directions and goes in the other direction, our graph is going to look like this blue line. And in this case, the slope is negative, and what that means, it's still a uniform slope, it's still a straight line, so the velocity is still constant, but now it's going in the opposite direction, it's going in the negative direction, because the sign of the slope gives us the sign of the velocity, and in this particular case, in one-dimensional kinematics, the sign of the velocity gives us the direction. And then our last equation here that we can glean from this, that we can get from this, is this guy right here, xf equals x sub 0 plus vt. Now, this actually comes from our equation here, delta x over delta t. So delta is xf minus xi. So v is equal to xf minus, or excuse me, whoops. Let's erase that. xf minus xi over delta t. So I'm going to rearrange this a little bit. I'm going to multiply delta t by both sides. So they're going to cancel out over here. And this is our first derivation. And when we derive formulas, we're simply getting a new formula from an old formula. We're rearranging it algebraically. We might combine 2 or 3 formulas together to get one formula to find what we want. So then I have delta t times v equals xf minus xi. I want to find an equation for the final position, so I'm going to add xi to both sides. And so I get xf equals v delta t plus xi, your initial position. Now again, we said that xi most of the time is going to be 0, so final position can usually just equal velocity times change in time, but it's not always going to be equal to 0. So that's where we get this equation right here. All right, guys, see you in class. Make sure to write down any notes or any questions you might have, and we will talk about them. Have a good afternoon.